going to go into greater depth about processes in the water cycle, specifically looking at catchment hydrology at a drainage basin level. This is for the OCR A-level geography spec 1.C, and I've highlighted the processes we're going to look at right here. I'm going to look at interception, which from GCSE you'll know is where precipitation is prevented from going to the ground by the trees who intercept it on the way down there. I'm going to look at some slightly more specific terms related to that. So through-fall is where the water that is intercepted, but it kind of falls through the leaves. So eventually it kind of makes its way to the ground and eventually ends up on the ground. We also have stem flow. This is where during really intense periods of rainfall, the actual water flows along the branches and down the stems of the tree. The most important one I want to consider at the moment, though, is where we have got water that actually gets intercepted but then gets evaporated away pretty quickly. And that's what we call interception loss. And so I'm going to look in a bit more detail about the factors that kind of alter rates of interception loss. One of them is tree species. So on the right, I've got a deciduous tree, it's an oak, and on the left, I have got evergreen conifers, which are pines and spruces. So the pines and spruces, they actually give off more in terms of intercept losses. So they lose more of that intercepted water back to the atmosphere. And the reason why is because they don't lose their leaves. They are evergreen, so they have their leaves all year round. Unlike the deciduous, which would lose it in kind of autumn to kind of protect itself from transpiration losses. So because it's got leaves all year round, it means it's got a surface, the evergreen, for water to be lost from, and therefore it's going to have higher interception losses. It's also got these pine-like needles, and what they do is they actually help the water collect and stick in the gaps, and therefore there is more water being stuck on the actual needles of the leaf, and therefore more of it gets evaporated back into the atmosphere. The other thing we need to consider is that vegetation type will affect it. So on the left, I've got my big deciduous tree. That is going to have a bigger surface area than the grasslands or the agricultural crops that you find on the right here. Therefore, those bigger surface area means more can be intercepted, and therefore more is going to be evaporated and higher interception losses. The other thing we'd need to consider is if it was windier, we would have higher interception loss rates because we've got higher rates of evaporation, and the same for temperature. Higher the temperature, higher rates of evaporation, therefore higher losses in terms of interception losses. I'm now going to move on to talk about infiltration, which on the most basic sense is where the water moves from the atmosphere into the soil in a vertical motion, so going downwards. We also need to know about the process of overland flow. That's where water goes over the surface because it can't infiltrate into the soil. And we're going to look at the reasons behind why that might happen in a second. Surface runoff or overland flow is what we call that. So there are a couple of theories about why overland flow happens. This is an example of water running over the surface because it hasn't been able to infiltrate. So we need to start with the idea that a soil has a certain amount of capacity, infiltration capacity. What I mean by that is this soil here, for example, could have the capacity that they could take about 15 millimeters of water and actually absorb that into the soil from the atmosphere in about 1 hour. So if it rained, I could pour 15 millimeters and within an hour that water would disappear. However, if I double or triple that, and that would be the example of having a really intense amount of rainfall. If this soil can only take 15 millimeters, there's only really one place it will go, and therefore it can't go into the soil, so it goes over the surface. So this is the idea that we could have overland flow because the intensity of rainfall is much bigger than the infiltration capacity of the soil. The other theory is slightly different, and it's talking about saturation. So on my diagram I've drawn here, I've drawn the water table. That is the level under the ground below which everything is saturated. So below that kind of dash line, the water, the soil is completely saturated. So to get overland flow, what I need is infiltration to happen initially, and that raises the water table. So that raises that level of saturation because all that water is gathering in there. That would therefore lead to the process of saturated overland flow, because what's happened is it's raised that water table, and therefore the water can't get into the soil anymore because the water table is right on the surface now. If we look at what's happening on this arrow here, and therefore it has to go over the surface. So that the saturated overland flow is where the water table rises, saturates the ground below, and so water can't infiltrate and therefore runs over the surface instead. Infiltration isn't just completely uniform, it also depends on the types of soil. So here's a kind of diagram showing different infiltration rates depending on soil. So if I've got a largely clay content soil, because clay is an impermeable soil, it would have a really low infiltration rate. So the higher percentage of clay, the lower the infiltration. On the opposite end of the scale, if there's more sand in the soil, that will have a higher infiltration rate, and therefore we'll get more water going into the soil. Another key process we need to think about is groundwater flow. So when water infiltrates, when it starts to go deeper into the soil and goes into the permeable rocks below, we call that percolation. That's the really slow vertical movement into these permeable rocks. But when it gets into those permeable rocks, it moves in a horizontal fashion. And as you can see on the graph here, on the diagram here, it's moving towards that stream because of gravity. And that slow horizontal movement through the saturated ground is what we call groundwater flow. So compared to other examples, we looked at through flow, which is where it goes vertically through the soil. Groundwater flow is where it's a really, really slow horizontal movement, and it's through saturated soil. Through flow is through the soil that is not saturated, so that would be above it. The last kind of area I'm going to look at is to do with snow and ice, and we call this the cryogenic processes. And the key idea here is that kind of we can lose water from ice, snow and glaciers, and when we lose it from any of those, we call that general idea ablation. So when in the summer temperatures go up, we're going to have losses from all of those, and that's going to be through 3 different ways. So we're going to lose it through melting, so that's where the ice becomes a liquid form. We're going to get it through evaporation, and the last one is a slightly complex process, but it's called sublimation. It basically means rather than the ice going into a liquid form and then into vapor, it skips a stage. So it changes straight from ice or snow straight to vapor. So those are the ways in which water is lost through the processes of ablation, and those are the 3 different ways in which that occurs.